Good morning, everybody. So now we are discussing about the modern control theory and its aspects in preliminary lecture. Introducing about, we should start the presentation. So it includes the modern and conventional control systems, nomenclatures used in modern control theory, state space modeling, state space model to transfer function modeling, and block diagram representation. Here, what actually the modern and conventional control theory states. The in control conventional control theory, it is basically based on the relationship of the input and output and represented in the form of transfer functions. In case of modern control theory, it includes the representation of the system with the first order differential equations, and later on for representing the system in matrix, so first order vector matrix differential equations can be used. On a specific comparison of classical control, that is conventional control system, and modern control system, so we can say that the conventional or the classical control system developed in between 1920 to 1950, while modern control theory came into existence in 1950 to 1980. In conventional control systems, the frequency domain analysis, which is based on the transfer function, is covered, while in case of modern control theory, it is based on differential equations, and time domain analysis is the mode of analysis. Here, conventional systems control system is for CISO systems, while it can be modern control theory can be used for MIMO systems as well. Classical of the conventional control system includes the input and output variables relation, while in modern control theory, input, output along with the state variables, that is one parameter is added actually, that is state variables, are accommodated or incorporated in the modern control theory. Robustness, that is the property of the control system. So if we are analyzing the robustness of a system, it highly analyzed in classical control system, while the modern control system have some restrictions. Controllability and observability cannot be concluded in case of conventional or classical control systems, while controllability and observability of a system is communicated or evaluated or can be observed in case of modern control theory. Optimality issues of a system are not predictable in conventional control, while optimality issues can be incorporated by modern control theory. It is the classical control systems which is highly evolved in the industries, while it is having some slow gain of popularity in case of industries, the applications of the modern control theory. These are, here we have states, we have defined some parameters of the modern control theory like states, state vector, state space system representation, state space model in terms of ODE, ordinary differential equations, and the numbers of the states relation to the order of the system or the ODE. If we define the state space model, it includes two equations or two parameters rather, that is state equation and output equation. State equation, that is this x dot equal to ax plus bu. Output equation is represented by y equal to cx plus du. Here the matrices A, B, C, D represents system matrix, input matrix, output matrix, disturbance matrix, and sometimes called feed forward matrix as well. Nomenclature for ABCD symbols is different for CISO and NEO systems. And state vector, that is X, is a column matrix if it is of nth n by 1. Input vector, it is also a column matrix of the order of m by 1. Similarly, state matrix, it is the matrix represented by capital A and it is of the order of n by n. Input matrix, it is of the order of n by m represented by B. Output vector Y, it is again a column vector matrix, and output matrix C, it is of the order of P by n. If we are interested to represent the system by the transfer function when dealing with the model control theory, then a system with loop gain Gs and feedback gain Hs, it is the system represented. So here it is the input signal, there is the output signal, this is gain of the system, it is gain of the feedback gain. So negative feedback system is considered here. ES, which represents the error signal and can be defined as this one plus or minus this. This signal is Hs into Ys. So Es equal to Rs minus Hs into Ys. Similarly, if we see the output of the system, it is Ys. So Ys is the multiplication of these two signals, Gs into Es. Now, if we eliminate Es from these equations, then a relation in between input, that is Rs, and output, that is Ys, can be obtained, which would be the transfer function model of the system. So Ys over Rs equal to one solution, we would be having Gs over 1 plus GSHs. Now, transfer function from state space model. State space model does mean two type of representations of the system, that is state equation representation and the output equation representation. State equation, that is again as defined in previous slide, xt equal to a plus axt plus but, and output equation is yt equal to cx plus dut. The representation or meaning of the system matrix A, B, control input matrix and control matrix and disturbance matrix. Taking the Laplace transfer function of transform of these two equations, that is the state equation and output equation, and Laplace transform is represented by I s into I xs axs plus bus. Similarly, ys equal to c x of s plus d u of s. If we eliminate the state, that is x of s, the transfer function can be shown as ys over us equal to output over input equal to c into the inverse of si minus a into b plus d. Considering an example, if we are having a system represented by state space representation, and here this is the state equation representation in terms of matrix, this is the output equation. For solution, as defined in previous slide, the transfer function can be solved by calculating C into Si minus A inverse B plus D. In this problem, we are facing that D is not present. Only system matrix A, B and C are present, and D is not there, so D can be considered as 0. So we have to simply calculate this first term of the equation, that is C into Si minus A inverse into B. So inverse of Si minus A is the thing which had to be calculated initially. So calculating Si minus A, simply this is the matrix. So calculate using Si minus A, and this is the result. Now inverse calculation can be calculated by calculating the adjoint of the Si minus A matrix and determinant of Si minus A. On solving, this is the adjoint of the numerator is the adjoint of the Si minus A matrix, and determinant is S cube plus 3S square plus 2S plus 1. Putting the values of matrices and solving this equation where D equal to 0, the transfer function can be calculated like this. Now, if we are interested to represent the system model, state space model in terms of block diagram, so that by block diagram representation or signal flow graph representation. So in this lecture, we are considering about the block diagram representation of a state space model. It has 4 steps. First, that is draw n integers blocks and assign a state variable to the output of each block. Blocks does mean the derivative of the state or number of state equations. So how many number of state equations are there? Like that is maybe the order of the, that is generally equal to the order of the system. So if it is a order of n, so n integers of 1 by s gain, that is like this, should be arranged, and number of state variables can be assumed. If you are having third order of system, then 3 states would be there. So states nomenclature would be x1, x2, x3. In case of step 2, input to each block, there is summing input. So this is your integer, so s raised to 1 by s gain block, and left to this one we have to consider the summing point, summer. Then in step 3, use the state equations to connect the state variables and inputs to the summing elements through scaling operator blocks. One thing that should be clear, that this is the integration block. So the output of this integration block would be, if it is xt, then input would be x dot t. This is the basic thing that have to be kept in mind always. So if it is if you have considered a third order system, then 3 states would be there: x1t, x1 dot t, x2t, x2 dot t, x3t, x3 dot t, and connected in the given fashion according to the problem, right? Now, for more clarity, we should consider an example of second order system. It is asking about the block diagram representation of the system. So this is second order system. Here this is the state equation and this is the output equation, yt. Exploring the state equations, x1 dot equal to a11 x1 plus a12 x2 plus b1 ut. Similarly, x2 dot t equal to a21 x1 plus a22 x2 plus b ut. So these are the expanded form of the state equation. So two states are there, x1 and x2. So the output equation is same as in case of this. If we are expanding this in representing in terms of differential equation, so as c1 x1 plus c2 x2 plus d ut. Right? Now, for making easy to do the block diagram, we have rewritten the state equation and output equation. Both of the state equations of first order differential and output equation is this one. Now consider one by one state equations, considering x1 equal to a11 x1 plus a12 x2 plus b1 ut. So if we are considering two states, two differential equations, it does mean the input to the integrating block x1t x1 and output is x1t. This is x1 dot t, this is x1t. Similarly, input for this second equation x2 dot t and output is x2t. This is the primary work we have to do. Now we should consider first equation x1 dot t equal to a11 x1 plus a12 x2 plus b1 ut. a11 x1 plus, here is the summer, so x1 dot t equal to what? This is sized from here and a block of a11 gain is connected to the summer. So this would be a11 x1 plus a12 x2. So again x2 is sensed from here, a12 x2. So both of the signals are added here for getting x1t plus b1 ut, right? So this basically block represents the state equation x1. Similarly, for x2 dot equal to a21 x1 plus a22 x2 plus b2 ut. a21 x1, this means x1 is changed from here and multiplied by the gain a21. So the output would be a21 x1. x2 dot t equal to a21 x1. So this is the multiplication added to this summer. Similarly, a22 x2. So x2 is changed and multiplied by the block a22 gain and added here. And one more, that is the b2 ut. b2 and changed to ut is there and it is again plus, that is added to the summer. So output x2 t equal to x1 a21 plus x2 a22 plus b2 ut. And this is the equation which is synthesized here. Now considering the output equation by t, it is c1 x1 plus c2 x2 plus d ut. c1 x1, that is the multiplication, x1 sensed and the c1 block, so c1 x1 is here plus c2 x2 is here plus d ut. So d ut is this one. So this particular represents the output equation. So this is the block diagram representation, general block diagram representation for a system represented in a state space model. Now taking another example of third order system. So this is the representation of the system with the state equation in matrix form, and this is the output equation. So expanding this one in differential equation, x1 dot t equal to this 0 plus x2t plus 0 plus 0, right? Next, x2 dot equal to 0 plus 0 plus 1 to x3 plus 0. Okay. x3 dot t equal to minus 13 x1 minus 19 x2 minus 7 x3 plus AUT. So this is this one. Now output equation by t equal to 26 x1 plus 13 x2t plus 0 plus 0. So this one output equation. Now coming to the block diagram representation. So for this one initially we have to consider that 3 states are there. So then 3 integrating blocks should be there. 3 integrating blocks should be there. And that is now, and output of an integrating block is state, an input to a integrating block that have to be considered at the output differentiation of the state. So 3 integrating blocks we have considered 1 by s, 1 by s, 1 by s. Output is x1, input is x1 dot, output is x2, input is x2 dot, output is x3, input is x3 dot. Now as per our differential equation representation, x1 dot equal to x2, x1 dot equal to x2, so x1 dot equal to x2, that is there should not be any gain in between, and that is rather 1. So simple wire can be connected in between x1 dot and x2. Similarly x2 dot equal to x3. So these two equations are configured in block diagram representation. Similarly for consideration of x3t, it is minus 13 x1. So x1 is sensed here, minus 13 gain is connected here, and it is applied to the summing point. And next term is minus 19 x2. x2 is sensed with gain block of minus 19. It is again added. Similarly minus 7 x3t, x3 is sensed with gain minus 7, and it is added here, plus ut. So simple input signal, we have forgotten about writing the ut signal input. So x3 dot is configured. For configuring or structuring the IT output equation by t, that is 26 x1t, x1 can be sensed from here and with a gain of 26 they applied to for getting the summation to the summer. Similarly plus 13 x2, x2 is sensed with gain 13, it is added here. So output equation yt is this. So in this way we have covered how we can represent a system by block diagram representation, by transfer function. One state is defined in terms of state space model, and what are the basics of the state vector, etc. terminology used in modern control theory. Thank you.